Unreinforced masonry walls are very vulnerable to the out-of-plane actions, even more so at the higher levels of a building where the accelerations are large and the walls relatively slender. In a building, the supports of the out-of-plane loading masonry walls are subjected to a motion that is filtered and amplified by the building structure. As a consequence, this motion can have quite different characteristics with respect to the ground motion. In this paper, we focus on the response of a single wall subjected to relative input motions at its top and bottom supports. We model the wall by discrete elements. Every unit is a distinct block, and all the masonry deformation is lumped at the interface between the blocks. To study the effect of the relative support motion on the wall, the top and bottom input motions are different. For the study, 10 natural ground motions covering a wide range of p-ground properties are selected. From these ground motions, artificial input motions for the wall supports are generated by using signal processing techniques. Of these motions, we control the difference in phase and in amplitude. Let's take, for instance, the Nahani record. Non-synchronous support motions are generated by using the Hilbert transform. Three scenarios are created: the one in which both supports are in phase, plus two in which they are out of phase by 45 degrees and 90 degrees. Similarly, three other scenarios with support motions of relative amplitude are created by amplifying by 0, 1, and 2 times the difference between the top and the bottom supports. Different wall configurations are investigated. Let's focus, for instance, on configuration number 8. An incremental dynamic analysis is carried out, and the average support acceleration at which the wall fail is searched. Repeating this for all the records, a fragility curve is built. Using this strategy, fragility curves resulting from each scenario can be compared. Using for comparison the median values of the fragility curves, the conclusion of the study can be drawn. Looking at not synchronous support motions, for most of the studied configurations, the acceleration capacity of the wall decreases up by 10%, and by 20% when the wall supports are in quadrature, which means they differ in phase by 90 degrees. However, for configurations in which the level of overburden is high, the wall capacity can dramatically drop by more than 50%. And a similar conclusion holds for support motions that are in phase but of relative amplitude.